This Inform seminar. My name is Ben Lev, and I'm very, very happy to present an old friend of mine, Leibfried here, who is a pioneer in quantum computation with ions. Has been working on that for the majority of his career. Of course, not all of his career. So he got his diploma and PhD from the Ludwig University in Munich. And he stayed there, I guess, sort of there, the Max Planck Institute of Quantum Optics in Garching with him. She was a laureate, where he worked on doing precision spectroscopy of hydrogen. So before the frequency comb, if anyone studied about frequency comb, they have these huge rooms with all these lasers locked together to do spectroscopy of hydrogen. And now it's much more simple, but it's a good learning experience that we took to do a lot of other things in quantum computing science, like going to NIST, Boulder, with Dave Wineland, another Nobel laureate, in what was that, 95, to do his postdoc and work on ions. He went back for a while as a assistant professor at the University of Innsbruck, worked with Michael Blatt, another pioneer of ions. So he basically covered all the ion groups possible in the world. And around 2001, went back to NIST Boulder, where he became one of the team leaders for the ion storage group, which he'll tell you about. So DE has won many, many awards. Fellow of the APS, American Physical Society, for quantum information contribution with ions. He's won several awards from the federal government. He's an employee. This is in the lab. One is called the Arthur Fleming Award, and 3 Department of Commerce medals, 2 bronze medals in 2018 and 2021, and the gold medal in 2023. So we're very, very pleased to have him speak.
Thank you, Ben, for having me here. Very kind introduction, and thanks to everyone also in advance.
Can everyone hear okay?
For showing me your cool experiments and all this stuff. It's really great fun to be here to just see what's going on, and all that. So I'm very grateful. In any case, as Ben already told you, we've been working in the ion storage group at NIST on the quantum control of atomic ions most of the time. And lately, we're also working on molecular ions. And my talk will have 2 parts. One will tell you what's going on with the atomic ions for quantum information processing. And then the second part is actually an answer maybe to the question of, okay, where's all this quantum stuff going? Because we are able to almost change the paradigms of how we can look at molecular ions in isolation and precision. And we're basically using quantum information techniques for that. So if nothing else comes out of quantum information with trapped ions, I think at least this kind of spectroscopy, which can also be applied for high charge times, by the way, that's not what you're doing, but other groups are very successful in that. This is something that will probably remain even if things turn out to be not the best qubits. So just for introduction, I want to at least explain in a nutshell how an ion trap works. The ones we're using are so-called radio frequency ion traps, and they confine the charged particle in what we call potentials. These are time-dependent potentials, so this particle is oscillating all the time. And the way you get confinement, we call it a pseudo-potential, is if you think about an ion in such a quadrupole, and here are electric field lines, then there's only one place here where there's no electric field. Anytime the ion moves out, it gets essentially shaken around because of micromotion by these electric fields that change at a very high frequency, much higher than the typical frequencies of the ions. And this shaking corresponds to a kinetic energy, and you can just solve the free equation of an ion in its electric field, and you'll find out that you get a kinetic energy that looks like this. The factors are not important. Just note that everything here is positive, including the square modulus of the electric field, which means if the electric field goes to 0 anywhere, that's where the ion wants to be, because that's where the pseudo potential energy is minimum. And you can actually see here, this is a picture of Wolfgang Paul's Nobel lecture. He was the first one thinking about these protocols. When Wolfgang Paul was doing these experiments, there was no laser cooling. That came much later. And that meant that they need to have a really nice protocol everywhere. So this potential holds in hollow space. You can laser cool your ions, you can basically stay very close to zero. And probably everyone remembers if you're close to a zero in some function like this, there's a quadratic surrounding. And so we can basically take our ion traps and unfold them into a plane, which is much easier to microfabricate. So the electrodes are just in a single plane. There's an RF and there's ground. And then the field lines essentially turn around like this here, or they come in from this ground here like that. And at some point, they just can't bend hard enough anymore. They have to go over here. And that means there are field lines that go in this direction and in that direction. And the only way they can agree with each other is by having a zero here. So locally, we'll have a trap here. And by the way, these dashed blue lines are the so-called pseudo-potential equipotential line. So they correspond to this expression here. Where are the equipotentials of this? The first demonstration, this is the theoretical proposal here. And the first demonstration with atomic ions was also done at NIST quite a while ago. It was a linear trap. This was the end cap. There's another end cap, everything in the plane, of course. And the ions were confined in here. And as you can see, this is basically, if you take an imaging system, a very good lens, and a CCD camera, you can take pictures of ions as they fluoresce in their Doppler cooling light. And 1, 2, 3, I think this is 12. You can also see if you just fill too many ions into this potential, change the flash out. In any case, this is how we can trap ions in microstructured traps. To do quantum information processing, we always have to think about what are qubits. So for ions, these are 52 longest atomic states of an atomic ion. It would be either hyperfine ground states, then the T1 times, how long does it take until an excited state decays, so it's essentially infinite. Or it can also be grounded metastable, like these states, that would be an optical qubit. And for those, the typical lifetimes are on the order of a second or so. In either case, we can do single qubit rotations, and probably most of you are pretty familiar with how that works. I'm not going to talk about it very much, but essentially you can take one of these qubit states here and rotate them with basically arbitrary coefficients, complex coefficients in front of it, so laser rotation, and of course the modulus P1, and that defines the Bloch field. So you can move your state around on the Bloch field. More interesting maybe is how we do qubit gates in ion traps. Essentially, just taking the basic states here again, we would like to apply an operation, for example, like this so-called state gate onto this set of states. And I'll explain a little bit how this is done in an ion trap. We actually use some motion to do that. And the basic idea is, this is the simplest instance. You trap two ions in such a trap, as I've shown you earlier. And these two ions, they are basically like balls and springs. They repel each other due to the Coulomb force, and you get two axial normal modes. So either the ions move in sync with each other, the so-called center of mass mode, or they move in and out, the stretch mode. If you now apply a force to the ions that is state dependent, so if you're in spin up, let's say it points to the left, same for this ion here. But if you're in spin up and spin down, one points to the left and one to the right. And then you're tuning that force such that it's close to resonance with the stretch mode, but not quite there yet. So if you do that, and you think about it, here there's no differential force, so you cannot pull the ions apart and put them together. While if you have different states, there will be a differential force. Here they're pulled apart at this moment in time. And in this case, they are pushed together. Again, for the same, it's not doing anything. So you can excite this stretch mode for ion states that are different. And you cannot excite it for ion states that are the same. The only other ingredient that you need now is that you're not going exactly on resonance. You're actually detuning the force slightly by a small detuning. This is like you're pushing a kid on a swing and you're not quite doing a good job. So after a while, the swing and you're pushing it out of phase and you're actually breaking the swing down. And maybe not surprisingly, when you think about how this looks in position space, that's shown here, here, and then in phase space, you can also make a diagram. Basically, the swing goes up, and then you break it down again, and then it starts all over. In phase space, so this is the position here, this is momentum. The ground state wave packet, let's say, describes a circular path. And this area here of the circular path is actually the phase that the quantum state picks up. The basic idea is if I have two coherent displacements that are not parallel, and I'm not only adding these two displacements as the total operation, I will also incur a phase that's given by the area that these two enclose. So if you do this in a circle, you will get the circular area. If you do this once, you will come back to where you started. So the motional state gets entangled with the spin state when you're somewhere here. But then at the end of the day, all four are the same. And the effective gate that we can get for having just the right area here corresponding to perhaps is exactly the gate I first showed you. So you may have heard that people do so-called Roman-Sorensen gates. And essentially the picture for those is the same as long as you make a basis transformation. So rather than looking at the cubic base states, we will look at plus minus. These are just states on the posterior equator. And for that, the same picture holds. This is how we can do gates. And so now we have a complete set of gates. We just do rotations on the carrier for single cubic rotations, and then we can use this kind of a universal gate to do the two cubic gates. And you can then build anything you want out of that. So how should this please scale to a large system? The basic idea that we are following is first described in this paper here by Dave Wendland, that some people call the Bible of ion trapping. In any case, this is where you can find this. And it starts out, in our case, by having an array of these surface electrode paths. So cross section through here, for example, we come back to this picture that I already showed. The ion will be at the 0 of the hour electric field, which is produced by these red electrodes. And then we have what we call control electrodes. These are these green electrodes, and by changing the potential, we can push the ions up and down in these channels, or the ions. So for example, if I make this electrode more positive, it will repel this ion harder and push it. We also use two types of ions, a data ion and helper ion. Right now here, you just see helper ions, but I can bring in a data ion. I also should mention we have junctions here. So we want to be able to produce electric control fields that help data ions together in arbitrary combinations. We call that all-to-all connectivity. And that's why we need junctions. We basically have to treat the ions like they're wagons on the railroad, and we want to couple them together in arbitrary ways. In any case, if we, for example, put in another RF potential on this paddle here, we can make this a strong tunnel for the ions. And if I send an ion down this path now, it would actually go around the corner and come here. So by having these switchable RF paddles, we can decide which way we go in such a junction. And then, for example, doing a two cubic gate, what we would do is we would bring in two ions. They can be pooled with this ion here in the middle that we call the helper. So we can make use of the fact that they have Coulomb interaction. They're just repelling each other due to their charge. So no matter what the qubit state is, that will happen. And that means I can laser pool this ion in the middle here, And these two will just go along to a certain degree that I will talk about a little bit later. We have to play some tricks, but essentially that's how it works. And so in this way, we can use the helper for cooling, but they're also good for other tasks. And that's something we're exploring right now. You can actually also use them to prepare and read out your qubit ions. And that has some advantages. Essentially, if you directly pump these ions, you will have spontaneously emitted photons. And those photons can go anywhere. So if I prepare this ion here, it could actually have scatter onto this ion. And if ion is in an important state that I want to preserve, it could actually be decohered by being hit by a photon that's emitted from some process that prepares the ion directly. If we do it indirectly via the helper ion, we don't have to encounter these gray photons because these photons from the helper ion are quite different, and so they don't really interact with the qubit ions. That's how you can do readout and cooling. So, in any case, basically, the architecture we're thinking about would consist of this kind of confirmation, just 3 ions, 1 helper, 2 qubits. So you can bring the qubits in, you transport them, not everything goes right, but now you can cool on this guy, and then we're ready for a 2 qubit thing. And we can also read out by coupling these 2 ions together and then reading out the helper. And that will not affect other qubits. That's the essential idea. So to tell you about the state of the art, I actually have to draw on other people's work. This is an archive paper that appeared shortly, and it's from the company Continuum that grew out of Honeywell. And what they're doing here is they also use small packets to get basis 4 ions. They have a fantastic clean room, Honeywell does, that can produce these really complicated traps. So here's a trap that basically they call it a racetrack. It goes around like that, and they can shift up to 32 qubit ions, and then also 32 helpers, because in their architecture, every qubit has a helper. Around this racetrack, they can do the gates, as I explained to you roughly, they're doing enormous versatile gates, so on the plus minus states. And they can move these ions past each other by basically rotating the potential, so they can bring them together in arbitrary ways. And in this way, they were able to really demonstrate a lot of different circuits. And you can see some of these take actually on the order of tens of seconds. So you need very long coherence times to do this. And also you shouldn't use your ions within 20 seconds. You should have them much longer. Lots of gates. Single qubit gates, 2 qubit gates, and also measurements. These are actually in-circuit measurements, and they have to worry about the spontaneous because they're not using the helper readout trick yet. In any case, what they were able to demonstrate is that they have a single qubit gate infidelity of about 10 to 2.5 times 10 to the minus 5, and the 2 qubit gate infidelity is 2 times 10 to the minus 3. You need a lot of laser power to do this, 5 to 10 milliwatts per gate beam, and there are 5 to 2 gate beams here. So on the order of hundreds of milliwatts. And the really nice thing about this demonstration, maybe the nicest, is that they did very small things with just a few gates and very large things, and the fidelity didn't change. So it doesn't depend on how long the algorithm is or how many qubits participate. The gate fidelity you see in isolation in the system is also the gate fidelity when everyone works together. So that's a really great demonstration. And it took a lot of effort. They're basically having a 10 times this large budget and group as we have at NIST. So they're really fed up for doing this. In any case, we are still not quite there yet. This is just 32 qubits. If you want to build a quantum information processor that can really do something, nobody would then disagree whether there's a quantum concurrency or that. So you probably want something on the order of 1 million logical qubits, which is a lot more than 32, obviously. And also the errors on state preparation and the operations and the measurement should be on the order of 15 marks. So that's also not quite reached yet. The 2 qubit gates are around 10 to the minus 3, so with it's still some work to be done. And then finally, in order to do error correction and be fault tolerant, you probably need only one of 10 physical qubits per logical qubit. So this big machine, Manhattan of ions, would have on the order of 10% gains physical qubit, so lots of ions. The rest of this part, I'll explain to you quickly what we're doing at NIST to at least get closer to this point. So our specialties at NIST now is that we do all the gate operations with near field and microwave power, with the near field of microwave codes. The advantage of that is that you can use relatively simple electronics and replace really complicated laser systems with them. We also want to extend the helper qubit role, which was just for cooling in the legal setup, to also do these other things. And basically, we can do indirect quantum logic readout and state preparation, as I already mentioned. This is in this paper here. I'm not going to focus on that. And then finally, what we also would like to do in the fullness of time is to integrate all the functionality, so laser beam and everything into the trap. So when the trap gets larger, these detectors, for example, will scale along with it. So first of all, the electronic operations. We actually have an expert for this in the room, on Bert, who was a PhD student a while ago. In any case, these experiments were done with lithium at time ground states, so the qubit frequency is about 1.3 to 1.6 gigahertz. So you need sources 3 to 1.6 gigahertz, and we can use such sources and switches and things like that. It makes it all feasible. And also get rid of our main problem when we do Raman transition, which is the H. And if you have an optical qubit, the upper state has a lifetime. Secular time, so that's also that can be a problem. This has potential that integrated in within the chips, and so basically all these electronics are in that part of industry. The way it works is shown here. Oh, I should also say we still need lasers. Of course, lasers allow us to do optical pumping, remove entropy from the system, cool the ions to the emotional form state. So we can't get completely rid of lasers. But we only have to do low power lasers for the remaining tasks if we can do the operations with the microwaves and RF electrons. The basic idea also relies on the fact that we can make these traps very small, because essentially, if you think about the free space wavelength of these tones here, it's centimeters. So having a gradient, something that moves the ions around with its force, is very, very hard. However, if you're close to, say, a wire, then you get a gradient just from the fact that there's a near field around the wire. And so essentially, you use 3 wires and you phase them up and put the right current through them. You can create a situation where you have a strong gradient here, where the ion is, and at the same time, almost no field. So you basically try to set up a zero crossing the B field here, where the ion is, and then have a strong gradient. If you're not doing that, the ratio of how you would drive the carrier to how you would drive the sideband that can move the ion around would be on the order of 3 times 10 to the minus 4, so very weak. Therefore, it's important to have zero. Once you get that, you can do essentially the same gates that have been done with lasers with microwaves. And one demonstration that's in this paper showed that we can do the 2-qubit gate. I'm not going to go into the details how it all works. There's lots of technical stuff. But in any case, the ions were about 30 microns away, so we get fairly strong gradients. And we were able to have a gate error that's commensurate or with the best laser gates that exist at this point. We still have to work on the gate duration, so that's kind of foolish, but it's not too bad. In any case, we're hoping that this will eventually be the way how we can do a lot of gates in parallel in a big processor. And again, now you just scale gigahertz type electronics where stays. It's just, we'll see how it goes. Another trick that we learned to use is actually buried in the nitty gritty of how iron crystals work. If you think about the normal modes of, say, a beryllium and a magnesium plane, they're quite different in mass. It turns out that one mode has a very small participation shown by this vector in the normal mode compared to this. So if I want to do all my cooling on this ion here, there's a problem because it's not really participating in this. Cooling this mode would be pretty hard. And for free ions, it's even worse than that because there's a switch mode here. And the middle ion doesn't participate at all in that mode. So what to do? Well, it turns out since we have an ion trap that has a lot of electrodes, we can not only apply trapping fields, we can also apply modulation. And so what we can do is we can basically produce an oscillating potential for electrodes that doesn't oscillate at any of these normal mode frequencies, but rather at the difference of the normal mode frequencies. This is some fairly complicated math, so don't worry too much about it. Really, all you want to look at is this factor in the end. Essentially, each ion participates to a coupling of these two modes in the sum here, and you would like to have all the factors in the sum to have the same sign. For coupling this mode here and this mode, the problem is that this participation and this participation has opposite signs. So if you do nothing, basically you would have destructive interference. But what we can do is we can take the curvature factors, these factors here, and create just the right potential. So now you can couple this mode because the curvature here is not an even function. And then the product of these two is also not an even function. The total is an even function, or in other words, the sum is constructed and we can couple these modes. And this really works great. It's actually a coherent coupling. So you can, for example, if you prepare one of these modes in the one quantum state, so one motion in it, you can swap that quantum pretty much completely into the other mode. That's what's shown here. This is the probability to find a quantum in one mode, and this is the other mode. And as you can see, they switch roles when you have one in this mode, it's gone in that, and vice versa. And it's really nice and coherent. We can actually do this many times, that's shown here. And essentially, if you do it just through half a swap, and it's a beam splitter, this is on resonance right here. So it would be a beam splitter, you would have half a quantum or one quantum in superposition in one mode and the other mode. You can swap, so you can exchange the energy between the two modes. You can also do a double swap, which essentially does nothing. You swap into the other mode and you bring it back. It's almost like nothing has happened. There's actually a phase factor, but don't worry about it. In any case, we can do this coupling. Oops. We can do this coupling, and you can see it's fairly good. It's about the population losses on the order of times 10⁻³ . In principle, you could think about coupling bosonic modes of each of these normal modes, bosonic mode in this way. And this is basically one way to do that. For us, it has a very mundane application. We just want to pull all the additional modes when on the helpers. And we can show that we can do this using this coupling. Forget about all the kinds of coherence and so on. We just use exchanging. So here's a swap and here's a swap. We can essentially cool the mode that has strong participation and then swap to a mode that has a weak participation. These would be these two modes here. We first swap the C mode with the X mode with the C mode, and then the Y mode with the C mode. And in this way, we can pull all three of them very close to the ground state. Here is N bar, some order of the bar for the worst move mode. And you can do the same thing for the axial modes, 3-ion crystal. So now we can solve this nasty problem that both per se does not participate, the magnesium cooling does not participate in. You just couple the modes together, and in this way we can do all of that. That should allow to shrink the basic package that Peter is using with 4 ions to maybe 3 ions. Not a big win, but I think how the large number of people that actually comes in. The final thing I want to talk about in this part of the talk is that you can actually integrate your detection directly into the chip. So this is shown here. This is a cryogenic experiment. In the particular experiment I'm showing here, the temperature of this detector was 3.5 Kelvin. This is a superconducting Neander wire detector. I'm not going to tell you exactly how it works, but essentially we had to go that low in temperature, so it actually is doing what it's supposed to do. The idea here is that if you have an architecture where you can transport the ion out, the video graph in the demonstration, you can take the ion and you can put it on top of this detector. And then without any optics, you can just excite the fluorescence of this ion, state-dependent fluorescence. And depending on which of the qubit states it's in, it will give you this kind of a histogram, the dark histogram, or the bright histogram. You can do different ways of discriminating these states. One is to just set thresholds, get a certain number of times you declare to be dark, and get more than that, you certain amount of less, you declare to be dark. If you get more, you declare to be bright. Or you can actually look at the arrival time and call that up the photons into a Bayesian detector. This gives you slightly different results, but essentially we were able to show a readout error with this detector on the order of 10 to the minus 3 in 46 seconds, which is pretty good. And essentially the nice thing about these detectors is, oh yeah, one thing I forgot is in the meantime, we've also found a better material. So this was a polysilicon Neander wire, and now we've switched to niobium titanium nitride, and now we can run this detector 6 LE, which is a big win because 3.5 means you have to go under work, you go strictly. Now we can actually stay like that, which just for practical reasons is nice. Essentially, we don't need imaging optics here, and you can imagine that you can integrate these detectors pretty much anywhere in the trap array. If the trap array increases in size, your number of detectors will also go up. While if you're detecting with the lens has a certain field of view, and that will not go up. It's really hard to scale at some point. So essentially, you can do parallel readout with minimum crosstalk using these detectors. That's the hope, at least. Again, this is what other people do, or I think we all should go, and that is integrate the optics into the trap as well. So what you can see here is for calcium ions in particular. At 729 nanometers, you can build waveguides inside the trap, and then you have gratings. These gratings couple the waveguides to free-phase beams, and the free-phase beams can then illuminate the ions top of the structure. The beams come in with waveguides, and then, for example, here in zone 2, we would have suits that converge onto the ion, and we can run it to cubic gate. Again, this is a proof of principle demonstration, but it was possible to do something like a gate fidelity of 29993. So not the best in the world, but some integrated optics. And this is really progressing nicely. There are, in the meantime, waveguides for all calcium wavelengths, for example. And the shortest unique product is 397 nanometers. People debate whether that is visible or ultraviolet. It doesn't matter, as long as you can build the waveguide. And so the hope would be the traps eventually will look like that, and that's the next thing we want to demonstrate. We want to put all of this together. We want to use the microfabrication, so everything's basically self-aligned. Your laser beams are just in the right place. fabrication, no one has to tweak them. You will have electrodes to do the microwave and RF things. You will have superconducting detectors in some places, and finally, we have got the right combination of helpers and data items. And if we could demonstrate such a basic building block, that would really, I think, open the way to further miniaturization, scaling, all that. We've just started a collaboration with Leibfried labs that really pioneered these waveguides to demonstrate such a unit. So that's basically the next thing we want to go to. So now I want to switch gears and talk about the other project, where I basically said, suppose I have some information processing is not good, or it's some other activity is much better. What can we learn? And I think this is an application that will probably stay around on logic control of any kind. Necessarily with molecular lines. Molecular lines are very suitable for this kind of control. So what is it all about? Before I even start, I want to give a big shout out to James Chow, my collaborator on this particular project. And James is actually more than a collaborator. Without him, I probably wouldn't have to talk about here because he really is on. You know, James, he's a force of nature in the lab. He was really able to fill out all the little things, dot the I's, cross the T's, and make all this work. There are also other quantum logic spectroscopy-based groups that do work with molecules, and I want to acknowledge them here. There are too many to go into details, but in any case, this is a growing field. I want to tell you what it's all about. So essentially, we all would like to extend our control of things, and one actual goal is to have molecules in the controls. Now that we can pull atoms and play all these great games with them, what about molecules? The problem is, first of all, you need to laser cool them. And even if you think about atoms, they need to be fairly special. So they have a cycling consistent, you can scatter many photons. Maybe you can tolerate a few recombers, but at this point, it's just too many lasers. And so most molecules don't even have a cycling. And the reason is that the potential of the molecule in the electronic excited state and the ground state, they don't look very similar. And that means the wave functions in the ground state, these are the vibrational wave functions here, they have overlap with any of these functions here. And that means if I ever excite the electronic position, then the vibrational state can actually change to go to any of these. And these are fairly long-lived, too long to really have decent cooling. You would have to wait on the order of milliseconds before they decay back to the ground state. So that's not good. And essentially what it means is you can maybe find a few special molecules where the upper state potential looks very similar to the lower state potential, and then these wave functions are still somewhat orthogonal. And maybe the number of recombers is okay then. But most of the time you can't do that. Basically, extremely special molecules can mimic the various ways. So what to do? One way of dealing with it is we can restrict to these data molecules. Another way that's very successful is to assemble the molecules from well-controlled ultra-cold atoms. And then the final way, and this is sort of the way we are going, is just to avoid the excited state. And so then you don't have spontaneous decay and you're not lost. But what that means is that you cannot observe any light, because this decay actually would deliver photon or fluorescence. But we're not seeing that if we always stay here. These decays, they're very long wavelength, so we would be really awkward. So what to do? Basically, we can use quantum logic spectroscopy. I'm going to explain how that works in the next slide here. Essentially, we use the tricks that we've learned. So first of all, we have two ions here again. You can select one of their normal modes and pull that to the electron state. So that's what's shown here. An active ion is some state, but motionally it's in the ground state. And of course, the ground state is a joint degree of freedom. And so this guy is in ground state, this one is in ground state too. It's a lot easier to see in this cartoon here, this 3D cartoon. But basically, one ion would start to jiggle, and the other ion has to come along because of the full interaction. And so either they're both cold or they're not both cold. What I can do now is I can try to excite a transition in the molecule. So for example, I'm trying to excite this transition, and this is a bit of a complicated slide because you have to watch two things at the same time. This is if you're not on resting, so you're not exciting this transition. This is when you're on resting, so you're exciting the transition. So two things happen here because it's on a side band. On the one hand, you're changing the rotational state, so compared to this one, it's rotating. And also you've excited the normal mode here. This is easy to see in the cartoon, but here in the level scheme, you actually have to look at this subtle change. The logic ion is also in the excited motional state now. And that means there's some energy in this motion, and I can take advantage of that energy when I look at the logic ion. So I now do red sideband, what we call a red sideband in the logic ion. If I'm in the emotionally excited state, that photon has enough energy to go to the ground state with the spin of the logic ion flips. While if I'm not in this excited emotional state, I cannot do that. I'm pressing. That means when I send in such a pulse, the spin flips here, the rotation is still conserved, but the motion is gone in the ground state again. And in the other case, when I was off resonance, nothing ever really happened. I always stayed in the emotional ground state, and the spin of this logic ion didn't flip. And that is my signal. And now ask, does the logic ion have a spin flip or not? And if I do that, I will either see fluorescence, in this case, say, or I will see no fluorescence, because the spin flip is happening. And that tells me, hey, I've excited this molecular transition. And in fact, since I haven't touched the molecular ion after doing this, but just directed its motion, its translational motion, it's still in this rotational state. So if and only if the molecular state was actually excited, logic ion will switch its state. And that gives me a signal that tells me, hey, molecular ion is in this rotational state, now it must be the final state of the transition. But otherwise, all of this would not have happened, and the logic ion would have remained in the state. So this is a non-demolition measurement of the state of the rotation of the storm for that to be defined. So to show all this is just what I'm telling you, and it's cartoons, but does it really work in the lab? We are using calcium hydride plus this molecule here. The reason why we do that is that it's a nice molecule for us. We can load our usual calcium atom, two of them, into the trap, and then we just increase the hydrogen background. It turns out when you later excite calcium plus, we just do Doppler cooling. This excited state energy is high enough that you can react with H2 and form a calcium hydride plus and one hydrogen slides away. Once you form this, the molecule decays into its electronic and vibrational ground state within a few milliseconds. So now you're basically in the state up here. And there are lots of other vibrational states. There are excited electronic states. And most importantly, there are lots of rotational states. So when I look at this here and I actually blow everything up, so now we have gigahertz distances, it's about 9.5 inverse centimeters, while these are 10,000, so a lot more. I can see this rotational separates. So this, for example, 3, 2, 1, and they have 94. So what to do about those? Essentially, at room temperature, a lot of these rotational states will be calculated. The molecule is in strong equilibrium with its surrounding, which will have to do to that for your radiation. And also, the proton here has a nuclear spin half. So each of these states actually protons spin up or down, and that gives you another degree of freedom. So these are, for example, they equal 0, 1, 2, 3, the subspace state. The way we can deal with that is that we first of all can apply a magnetic field. All right, we're about to say these little dots, they show that about 1.1% of the population is roughly in such level at 300 Kelvin or less. So if you go up in energy, of course, it's a Boltzmann distribution, it will be less. But this is the max you get. So lots of states where you have hydrogen possibly be. If we now focus on the J1 and also we apply a magnetic field, we can go to an intermediate regime. What that means is without an external field, these two spins, they have magnetic moments. One is the rotational magnetic moment, the dipole solving in circle. And if you have a spinning dipole, it will create a magnetic field. And then the other one is the magnetic moment. And they couple together. For a relatively small field, because these coupling energies are in the order of a few kilohertz, you can break this. And so now the two magnetic moments would rather like to follow magnetic field lines than decouple to each other. If you go in between, you can get rather uneven separation of these states. And in particular, there's one transition here that we call our signature transition. That is quite different in frequency from the other ones you, and that's actually the ones you concentrate. So for the J plus 1, for example, this is 10 kilohertz, and conveniently, if you go to J plus 2, for example, same magnetic field, it's 14 kilohertz, and it actually goes up as you go to higher J. So what we can do is we can basically try to drive these signature transitions and see whether we can catch the molecule in the act and arrest its state. So the way we excite them is rather simple. In fact, we can use this with the CW laser. Oops. We use one laser. Okay. We use one laser and send it to two different neurons to split the beam. And then we have a difference in frequency here that corresponds to the motional frequency. In our case, this is a few megahertz or 5 megahertz. And then there's this small kilohertz, which is top of that. And that kilohertz split corresponds to the signature transition. We shine in these beams, and if we can successfully drive such a transition, not only will the molecule change the rotational state, also the motion of the ions will be excited. And then we can detect the logic ions in the leaf state. So what's happening here? Essentially, we're trying to drive the signature transition. And if we can drive it, this, probabilistic view, small possibility that this has now gone. There's a small possibility that this has gone to n plus 1 and also switched to rotation state. There's still potentially all this other population. But the miracle happens because all these other states are labeled with no motion. So if we now ask our logic ion, is there motion or is there no motion? So is there a motional quantum or is there no motional quantum? And the ion answers yes, it's motion. We get a projection. And suddenly we are just in the final state of this transition. So now we've actually prepared the molecule in a pure quantum state. That's essentially how we can prepare them. And then from there, it's fairly simple what we can do to do, for example, spectroscopy. That's the last part of the learning. So you also, we do not always do the detection here. We can also just pull the motion back to one state rather than detecting, and that also creates entropy removal. I'm not going to go into details about this. This is possible as well. So, for example, now I want to detect the transition in the molecule and I want to do it very precisely. The side plans are nice to be able to say whether you make a transition or not, but they're also nasty because the motion frequency, it's a feature of your graph. And the graph is more stable, it also. You can still detect just pure transitions of the molecule by applying another trick. So suppose I want to know this transition here, but actually my laser beam is slightly off resonant. So I have a frequency offset of the transition frequency. Essentially, I'm not going to make this transition. If I then do my sideband, side motion, so now I'm 1 here, and I can ask the logic line, I'm 0, I'm 1, I'm out here. Mostly I'll see I'm on, I actually made this transition and I've decided the motion. While when I'm on resonance, something else, if we show the state up here, and this pulse has no effect. The initial state is no longer populated. And so I'm down here most of the time when I ask my logic, I'll say I'm in 0, and that means I've hit the resonance. And this is actually one of the signature transitions that was detected in this way. Here, grading 1, mostly 0. We can do spectroscopy of all the signature transitions in this way. For example, this is J plus 1 here, J plus 2. See that very nice shapes with contrast, and we can even do Rabi plotting, so we can apply this pulse on resonance right here for various times, and you can see how this molecule of Rabi plotting being different subspace states of J plus 1 or J plus 2. We can also check how coherent this is, and so we can, for example, frequency experiment, we do pi over 2 pulse, wait for some time, and then do another pi over 2 pulse with a relative phase, the first pi over 2. And you can see this relative phase reflected in whether we can show the logic item shows up in 1 or not. Like so, even after 15 milliseconds, we get a pretty good contrast for these random experiments, which means the rotational state is actually coherent for at least 15 milliseconds with some not too bad survival probability. So that's great, but it's not very interesting in spectroscopy. They're just making small energy splitting the speed of the magnetic field. We can also look at rotational transitions between different J levels. But for that, we need a different technique. That's where pulse lasers come in. Essentially, we're using a frequency pump for doing some spectroscopy. And to try the CW laser, first of all, do some feature for technical reasons, and then we split the beam up. We have 2 different wavelengths that can be shift the relative frequency of these 2 beams to each other. We also need a delay line because this is a pulse laser of 80 femtoseconds or so, shorter, and the pulse have to collide on the energy, so we need a delay line. The magic with frequency pump is that if you do a Raman transition, a 2-photon transition, basically say this quantum tube and that quantum tube has the right frequency to drive this transition. Because they're all equally spaced and they're just shifted relative to each other with the AOM, I can shift this over. This pair will also drive the same transition. And this pair and all of these pairs actually. So when the whole coherently works together, if there is no dispersion. So the phase of this light field here and the phase of this light field is the same. And that's what the mirror teaching for us. They ensure that when the pulses collide on the line, that all of these are in phase. So does that really work? In fact, it does. And you can do very nice character rotational Raman transitions with that. We do the state preparation, that I already explained. We do a compulse next, and then we do state detection. Here's an example for Raman transition. There's delta J plus 2 in a linear molecule. So we can only go from say 2 to 4 or 1 to 3 or 0 to 2. So in the case of 2 to 4, that's shown here, we can see very narrow features here. As you can see, the frequency offset between the comp lines is just a few hertz here. So that's pretty cool. We're doing a transition at a rather large frequency with an uncertainty on the order of a few hertz. The resolution is about 2.5 10 to the minus 13. This is something I wish I could have done on my hydrogen atoms when I was a grad student. Now we can do it in molecules. One final thing, basically, since these comp features repeat each other after one comp spacing, so for example, comp is about 80 megahertz, you would have to figure out which of the orders, and you can do that by just changing the spacing between the comp keys slightly and then finding the same resonance. This way you can figure out how many integers you're away from zero frequency. And you can nail down the absolute frequency here. We've done that for a few transitions, and basically calcium hydride plus went from a molecule that no one knew anything about to one where you can find these transitions with very high accuracy and get all kinds of rotational constants shown down here. We also found another nifty trick how you can measure the electric dipole moment of charged molecule. That's what we need. Usually, when you want to look at the dipole moment, you apply an electric field, but this is an ion, so it would just fly to the wall and you apply an electric field. Of course, the trick is to apply the electric field in an AC fashion. So the ion doesn't normally go, just quivers around. So it has to do with the molecule. I'll leave it at that if you're interested. You can read this statement. Because we did a few more things. And one is, right now I told you we have to find this state. And once in a blue moon, we get lucky and we drive the right transition, we get our motion running and everything's great. We can do an experiment for a short time. So for example, in J plus 3, the state gets, on average, you stay in J plus 3 for about half a second. But it takes a long time for the state to return after that to J plus 3, about 50 seconds. For J plus 2, it's a little longer and a little shorter until it returns. J plus 1 is still better, but all in all, it's a few percent. So it would be much nicer if we can somehow keep the ion in a certain rotational state. What gets us out of there is the blackbody radiation, room temperature experiment. Unfortunately, blackbody radiation has selection rules to its basically dipole transition. So delta J is plus minus 1. What we can do is we can apply a gatekeeper strategy. So first of all, we project the ion J plus 1, and then we can just keep checking in between doing experiments. And we excite motional quanta here, so we can go back and forth, or forth and back. And if we see these motional quanta, we're pretty sure we're still in J. So everything's fine, we continue with the experiment. If we fail, due to inspection rules, it should be 0 or 2, right? So we can check those. We would check these two, and if we indeed find the molecule in them, we will then bring it back using millimeter radiation, 70 gigahertz or 285 gigahertz. So we can bring it back to J plus 1. We basically plot the molecule state at the border, plot it back into the interior of the country. And if we fail, of course, then we have to keep searching. And we're back to the old state where we didn't do anything at all. And at some point, we will project the state, give it in 1, 2, or 3 again, and then we can keep the molecule prisoner as long as it lasts. Okay, so how well this? Essentially, here's a maybe not typical event or successful events where we basically prepared initially in J plus 1, and then you can see at this point in time it jumps into 2, we bring it back, jumps into 2 again, we bring it back, and so on and so forth. It actually turns out that going to 2 is much more likely than going to 0 because the blackbody radiation is much stronger. Going to 2 and lower is just a feature of the blackbody spectrum. In any case, we can recover the population by just gatekeeping about 40 times on average, and we only use this fact fidelity in detections and operating. So by making those better, you could maybe even improve on it. But practically speaking, it's an enormous advantage because the effective mean dwell time, for example, in J1 year is increased from 1.5 seconds to 25 seconds. And that becomes quite comparable to the time you have to wait to find it in 1, 2, or 3 again. So essentially, our useful fraction of experiments now is 5%, from 5% increased to 50%. So more than half the time we're actually doing experiments and not just waiting for the molecule to show up in the right state. That's great. And I already said that, but due to the black body radiation difference between those two transitions, we expect that this is about 4 times more likely than going to take placebo. That's what we see in experiment. So it's consistent with black body, which is probably our main driver. This is not the first time people see quantum jumps of gravitational. There was a great experiment by James Thomson, and he was still at 1 feet in a pen trap. All right, final thing. Okay, I should wrap. Final thing is the latest that we can do is we can actually use a comb, again, a telecom fiber comb, and then do some jerk pulse amplification and put it into a highly nonlinear fiber, shift the comb to 1450, 1440, 1450. You can see how that goes as power of the comb. And I'll just run through this. So wrap up. We essentially can see vibrational transitions, overtone transitions with the fourth overtone. And you can see that also very narrow lines that are essentially limited by the life of the upper state. So here you can see the upper state behavior. Okay, it's very close to definition calculated value. We still have to work on the systematics. Exactly what the frequency of zero field is. That's in progress. And finally, what I want to say is that all I've told you about calcium hydride would work for other molecules as well, so even for polyatomic molecules. And that brings me to the summary. You can read over it. Thank you for your attention. Do you have questions? Yes.
Very nice presentation. I have a quick question about the micro local control, because we know like using Raman beam, you can actually focus down to like really local area compared to microwave, which is hard to lens in. So how well you can over there.
Yeah. Of course, I have to suppress a lot of details, but there are several ways how we can suppress the ions directly. Essentially, it comes down to the fact that we have this zero crossing of the microwave field. Maybe you remember we want to work with a position of high slope and a zero crossing. So if we do this with the carrier, exactly at the zero, your Raman frequency should also go to zero. While if you push one of the ions out a little bit, so it's not at the zero, you can actually rotate it. And in fact, all of this is very nicely aligned because these are the same things that also define the electrodes and where the ion sits, makes it very stable. So that's how you can do individual addressing. You essentially just bring the ions that we don't want to address to the zero of the microwave field or the RF field, whichever one you use.
Thank you.
Are there any questions? Okay, so coming back to this scaling question at the beginning,
Sure.
Is your sense that the racetrack approach is the way to go? You think optical interconnects are more promising? What do you view as the way to get to big systems?
Yeah, I think all of the above. So probably you can extend. You also have to think about how large will the system be again, if you just extend the ion trap, and how can you connect, say, different wafers. So probably you can do all of that, but at some point it would be nice to actually have optical interconnects. And maybe at the last moment, that would be if you want to have entanglement over large distance. So what people call quantum networking. as I would call it, entanglement generation of such distance. So you will need both. So, and this is actually something I will probably know. I think we shouldn't quarrel about what Cuban is great and what's not great. Because in practical bits, there are so many different kinds and they all work differently. So I don't think atoms or ions or superconducting circuits or whatever will be the sole winner. We have to offer different tools. And they will play a role in this game, photons, as you mentioned.
Well, I have one more, I promise, only one. In the racetrack, how high are the ions above the surface?
About 50 microns.
They have spectred like laser beam right across 3 zones.
Yeah, if you, I'm not sure whether I have time to go back there, but if you look at the graph. Here we go. So if you look at that graph, it has this narrow part that we call the distance. This is exactly for the reason you mentioned. All these laser beams have to have a focus, and the focus is fairly tight, which means that they diverge rather quickly. So it's probably a scale or somewhere here. If this whole thing is a few millimeters, and so this is a fairly short distance. That's why they deal with that. It's not scalable. And that's why you would probably need optics on the chip itself. Locally create foci.
I can see.
All right. So thank you all for joining.